Welcome to this coding walkthrough. In this session, we'll be solving LeetCode problem number 865, smallest subtree with all the deepest nodes. Together, we'll explore the problem statement, analyze different approaches, and break down the solution step by step. Let's dive in. In this problem, you are given the root of a binary tree, and your task is to find the smallest subtree that contains all the deepest nodes in the tree. Let's break this down. The depth of a node is defined as the number of edges on the path from the root node to that particular node. A subtree, on the other hand, is formed by taking a node in the tree and including all of its descendants. Now, the challenge is to identify the smallest such subtree that contains all the nodes that are the deepest in the tree. The output will be the root of this smallest subtree. To understand this problem better, let's look at some examples. Consider this binary tree, where the input is represented as root equals 3, 5, 1, 6, 2, 0, 8, null, null, 7, 4. The tree structure looks like this. We have node 3 at the root, with its left child as node 5 and its right child as node 1. Node 5 has children 6 and 2, while node 2 has its own children, 7 and 4. Similarly, node 1 has children 0 and 8. This gives us a clear visual representation of the tree structure. The output for this input is 2, 7, 4. Let's understand why. The deepest nodes in this tree are nodes 7 and 4, both located at the maximum depth from the root. The smallest subtree that contains both these nodes is the subtree rooted at node 2. This subtree includes node 2 itself and its descendants, 7 and 4. Therefore, the result is the subtree 2, 7, 4. Here's another example for clarity. If the input tree is root equals 1, the tree representation is extremely simple, with just a single node, 1. Since there's only one node in the entire tree, it is also the deepest node by default. The smallest subtree containing this node is the tree itself. So, the output is 1. Now consider a slightly more complex scenario with the input root equals 0, 1, null, 3, null, null, 2. The tree structure here is unbalanced, and it looks like this. Node 0 is the root, with 1 as its left child. Node 1 has its own left child, 3, which in turn has a right child, 2. Notice how the tree leans to the left, with the deepest node being node 2. In this case, the output is 2. Since the deepest node in the tree is node 2, the smallest subtree containing it is simply the subtree rooted at node 2 itself. Finally, let's note a few important constraints and edge cases. The tree can have between 1 and 500 nodes, and all values in the tree are unique integers between 1 and 500. Edge cases to consider include trees with only one node, completely unbalanced trees, trees where deepest nodes are scattered across branches, and trees where all nodes are at the same depth. These considerations help ensure a robust solution to the problem. To solve this problem, we can start by considering a brute force approach. The intuition here is to first identify the depth of all nodes in the tree and then find the deepest nodes. Once we have these nodes, we could examine every potential subtree to check if it contains all the deepest nodes. To break this down into steps, we would first traverse the tree to compute the depth of each node. Then, we would determine the maximum depth and collect all nodes that reach this depth. Finally, for each node in the tree, we would check if its subtree contains all the deepest nodes. While this approach is straightforward, it is computationally expensive because checking every subtree repeatedly can take a lot of time. Specifically, the time complexity is n squared, in the worst case, as we are traversing subtrees multiple times, and the space complexity is n, due to the recursion stack. This makes the brute force method simple to understand, but highly inefficient for larger trees. Now, we can move on to a more optimized approach that uses a single depth-first search, or DFS, to track both the depth and the lowest common ancestor, or LCA, of the deepest nodes. The key insight here is that the smallest subtree containing all the deepest nodes will always be rooted at their LCA. This means we can solve the problem by calculating both the depth and the LCA in a single DFS traversal. To implement this, we traverse the tree recursively, and for each node, we calculate its depth while simultaneously determining if it is part of the subtree containing all the deepest nodes. By the end of the traversal, we return the node that satisfies both conditions. This method is highly efficient, with a time complexity of n, since each node is visited exactly once, and a space complexity of O, n, due to the recursion stack. This approach is not only elegant but also avoids the redundancy of checking subtrees repeatedly, making it a clear improvement over the brute force approach. Another alternative strategy we could consider is a top-down depth propagation approach. The intuition here is to propagate maximum depth information from the root of the tree down to its leaves. This allows us to identify nodes at the maximum depth while also tracking the LCA of these deepest nodes. To implement this, we would first perform one traversal to calculate the maximum depth of the tree. Then, in a second traversal, we propagate this depth information while identifying the nodes that form the LCA for the deepest nodes. While this method also achieves a time complexity of O, n, since it requires two traversals and a space complexity of O, n, it is slightly less intuitive than the single DFS approach. However, it avoids redundant subtree checks, which makes it more efficient than the brute force method. Ultimately, it provides another viable way to solve the problem, though it introduces additional complexity. The key insight that simplifies this problem is recognizing that the subtree containing all the deepest nodes is rooted at their lowest common ancestor. By combining depth calculation and subtree checks into a single traversal, we can solve the problem more efficiently. Using recursion, we return both the depth and the corresponding node for each subtree, which keeps the logic clean and easy to follow. Comparing the approaches, the brute force method, while simple, is inefficient due to its repeated subtree checks. The top-down depth propagation approach is efficient but slightly more complex to implement. The optimized approach, which leverages a single DFS, stands out as the most elegant and efficient solution, achieving O, n, time complexity while maintaining clarity. By focusing on the depth and LCA insight, we ensure that this strategy meets both performance and simplicity requirements, making it the ideal choice for this problem. This problem is about finding the smallest subtree in a binary tree that contains all the deepest nodes. Deepest nodes are those located at the maximum depth of the tree. To solve this, we start by determining the depth of each node. Using a depth-first search, or DFS, we traverse the tree, keeping track of the current depth for every node we visit. The depth of each node is stored in a hash map, where the key is the node itself and the value is its depth. As we traverse, we also keep track of the maximum depth seen so far. Once we've computed the depths of all nodes, we can identify which nodes are the deepest by finding those with a depth equal to the maximum depth. These nodes are stored in a list for easy access. Finally, the goal is to find the smallest subtree that includes all of these deepest nodes. For this, we use a helper function and post-order traversal to determine the subtree rooted at the appropriate node. In the helper function, we start by handling leaf nodes. If a leaf node is one of the deepest nodes, we return it as part of the subtree. Otherwise, we exclude it from consideration by returning null. For non-leaf nodes, we combine the results from their left and right subtrees. If both subtrees contain deepest nodes, the current node becomes the root of the smallest subtree because it connects all the deepest nodes. If only one subtree contains the deepest nodes, we propagate that subtree upward since it already holds the required nodes. By following this process recursively, we ensure that the correct subtree is identified. At the end of this traversal, the root node of the smallest subtree containing all the deepest nodes is found. This approach works efficiently by leveraging post-order traversal, which allows us to process the child nodes first before making decisions at their parent node. Combining this with the initial depth-first search ensures that we compute node depths without redundancy. To implement the solution, we rely on three key data structures. First, a hash map stores the depth of each node, allowing us to quickly check and compare depths. Second, a list is used to store all the nodes that have the maximum depth, simplifying the process of determining which nodes need to be considered when identifying the subtree. Finally, the recursive helper function encapsulates the logic for determining the smallest subtree, making the implementation both modular and concise. Analyzing the complexity, the time complexity is O, n, where n is the number of nodes in the tree. This is because we perform one DFS to compute the depths and a second DFS for the post-order traversal. The space complexity is O, h, where h is the height of the tree, as this is the maximum depth of the recursion stack. The algorithm handles various edge cases, such as a single-node tree where the result is the node itself, a tree where all nodes have the same depth, which results in the entire tree being the smallest subtree, and unbalanced trees where the algorithm correctly propagates results upwards. Starting with the example tree, we compute the depths of all nodes. For instance, node 6 is at depth 3, while nodes 7 and 4 are at depth 4. This makes nodes 7 and 4 the deepest nodes. Next, we perform a post-order traversal to determine the smallest subtree that contains these nodes. In this case, the subtree rooted at node 2 includes both nodes 7 and 4, making it the smallest subtree that satisfies the conditions of the problem. This demonstrates how the algorithm efficiently identifies the result by combining depth computation with a recursive traversal to propagate information about the deepest nodes up the tree. The given problem requires finding the smallest subtree that contains all the deepest nodes in a binary tree. This solution uses a depth-first search (DFS) approach to recursively calculate the depth of each node and determine the smallest subtree containing the deepest nodes. The subtree-with-all-deepest function is defined, and a nested helper function (DFS) is used to traverse the binary tree. The DFS function returns two values: the depth of the current node and the subtree containing all the deepest nodes. If a node is null, base case, the depth is 0, and there is no subtree. For non-null nodes, the function recursively computes the depth and subtree for the left and right children. It then compares the depths of the left and right subtrees. If the left subtree is deeper, the result propagates from the left subtree. If the right subtree is deeper, the result propagates from the right subtree. If both subtrees have the same depth, the current node is the root of the smallest subtree containing all the deepest nodes. Finally, the DFS function is invoked on the root node, and the subtree, second value in the tuple, is returned as the result. This approach ensures that the solution is both efficient and concise, with a time complexity of O(n), where n is the number of nodes in the tree, as each node is visited exactly once during the DFS traversal. Here, we begin our Java implementation of the problem by defining the main function, subtree-with-all-deepest. This function takes the root of the binary tree as input and relies on a helper method, DFS, to compute the solution. The DFS method is a recursive function designed to traverse the tree and determine both the depth of the deepest nodes and the smallest subtree that contains all of them. If the current node is null, we return a new result object with a depth of 0 and no subtree. Otherwise, we recursively call DFS on the left and right children of the current node. By comparing the depths of the left and right subtrees, we decide which subtree to propagate upward. If the left subtree is deeper, we return its result with the depth increment by 1. Similarly, if the right subtree is deeper, we propagate its result. However, if both sides have equal depth, the current node becomes the root of the smallest subtree containing all the deepest nodes, and we return it along with the updated depth. Now, to support the functionality of the DFS method, we define a helper class named result. This class encapsulates two pieces of information, the depth of the subtree and the reference to the subtree itself. The constructor initializes these fields based on the provided values. Additionally, we include the definition for the treeNode class, which represents the nodes in our binary tree. Each treeNode instance contains an integer value, a left child, and a right child. With these helper classes in place, our implementation is structured to efficiently determine the smallest subtree containing all the deepest nodes by leveraging the depth-first search approach. In this first example, we have a simple balanced binary tree. The root node is 3, which branches into two children, 5 on the left and 1 on the right. Starting with a depth-first search from the root node, we first explore the left subtree rooted at node 5. For node 6, since both its children are null, we return a depth of 1 and the node itself, 6. Moving to node 2, we process its children, node 7 and node 4. Both of these nodes are leaf nodes, so again, their depths are 1, and we return the nodes themselves. Since node 2 has equal depths from both children, we determine that node 2 is the root of the smallest subtree containing all deepest nodes in this branch, with a combined depth of 2. At node 5, we compare the depths of its left and right subtrees. The right subtree, rooted at node 2, has a depth of 2, which is deeper than the left subtree. Thus, we return a combined depth of 3 and node 2 as the smallest subtree root for this branch. Now, we traverse the right subtree of the root, starting at node 1. For node 0, which is a leaf node, we return a depth of 1 and the node itself. At node 1, the left depth is 0 as there is no left child, while the right depth is 1 from node 0. Therefore, we return a combined depth of 2 and node 0 as the smallest subtree root for this branch. Finally, at the root node 3, we compare the depths of the left and right subtrees. The left subtree, rooted at node 2, has a depth of 3, while the right subtree, rooted at node 0, has a depth of 2. Since the left subtree is deeper, we determine that the smallest subtree containing all deepest nodes is rooted at node 2, and the final output for this example is node 2. Moving to the next example, we consider a tree where all the deepest nodes are located in the left subtree. In this second example, the tree is skewed to the left. Starting from the root node 1, we traverse the left child, node 2. For node 3, both its children are null, so we return a depth of 1 and the node itself. At node 2, the left depth is 1 from node 3, and there is no right child, so we return a combined depth of 2 and node 3 as the smallest subtree root. Back at the root node 1, the left depth is 2, and again, there is no right child, so we return a combined depth of 3 and node 3 as the smallest subtree root. The final output for this case is node 3. In the third example, we analyze a tree where the deepest nodes are distributed on both sides of the root. The third example features a binary tree with 2 subtrees of equal depth. Starting at the root node 1, we traverse the left child, node 2. Since node 2 is a leaf, we return a depth of 1 and the node itself. Similarly, we traverse the right child, node 3, which is also a leaf, returning a depth of 1 and the node itself. At the root node 1, the left and right subtrees have equal depths of 1. When the depths are equal, the current node becomes the root of the smallest subtree containing all deepest nodes. Therefore, the final output is node 1. To summarize, our depth-first search function returns both the maximum depth and the smallest subtree containing all deepest nodes. By comparing depths at each step, we ensure that we identify the correct subtree in O(n) time complexity, making this solution highly efficient for binary trees of any size. The time complexity of our solution is O(n), where n represents the total number of nodes in the binary tree. This efficiency stems from the depth-first search, or DFS, traversal performed by the DFS node function. In the worst-case scenario, every node in the tree is visited exactly once, ensuring that the number of recursive calls is directly proportional to n. For each node, we carry out specific operations such as calculating the depths of the left and right subtrees, comparing those depths, and returning the relevant depth along with the corresponding subtree. Since these operations take constant time, or O(1), for each node, the overall time complexity remains O(n), combining the traversal and per-node operations. The space complexity of the solution is O(h), where h is the height of the binary tree. This arises from the space used by the recursion stack during the depth-first traversal. In the worst case, such as in a completely skewed tree, the recursion stack can grow to a depth of h, which equals the height of the tree. For a balanced binary tree, this height is approximately log n, while for an unbalanced binary tree, h can be as large as n. Unlike some approaches, this solution does not use any additional data structures beyond the recursion stack, meaning there's no extra memory overhead beyond the stack itself. Therefore, the space complexity is determined solely by the tree height, making it O(h). In terms of best, average, and worst-case scenarios, the analysis changes slightly depending on the structure of the tree. For the best case, which occurs in a perfectly balanced binary tree, the height of the tree is log n, leading to a recursion stack depth of O log n, and a time complexity of O(n), since every node is still visited. In the average case, for a typical binary tree, the height is generally closer to log n, resulting in similar O log n space complexity and O(n) time complexity. In the worst case, however, where the tree is highly unbalanced, such as in a linked list structure, the height equals n, leading to both O(n) space and O(n) time. Compared to a brute force approach, which might involve repeatedly calculating node depths and performing multiple passes with a time complexity of O(n) squared, this optimized approach calculates all depths in a single DFS pass. This reduces the time complexity to O(n), while maintaining the minimal space complexity of O(h). The big O justification for this solution highlights its efficiency. For time complexity, each node in the tree is visited exactly once during the O(n) traversal, and the constant amount of work per node contributes an additional O(1). Together, these result in a total time complexity of O(n). For space complexity, the only memory overhead comes from the recursion stack, which depends on the height of the tree, or O(h). This makes the solution both time and space efficient, especially when compared to less optimized approaches, and it performs well even with larger trees. When solving this problem, there are several common mistakes to watch out for. First, it's important to clearly understand the difference between depth and height. Depth refers to the distance of a node from the root, while height measures the distance from a node to its furthest leaf. Confusing these two concepts can lead to errors in identifying the correct subtree. Next, avoid inefficient brute force implementations that calculate node depths repeatedly or traverse the tree multiple times. This can lead to a time complexity of n squared, or worse, which is impractical for large trees and can cause time limit exceeded errors. Additionally, be mindful of edge cases. For instance, a single node tree, completely unbalanced trees, or trees with multiple deepest nodes at the same depth all require careful handling to avoid incorrect results. Another common pitfall is assuming the subtree containing all the deepest nodes is unique. In reality, there could be multiple valid subtrees, and failing to identify the smallest one can lead to incorrect answers. Finally, managing recursion properly is critical. If you forget to return both the depth and the corresponding subtree during recursion, your solution may be incomplete or produce the wrong results, and debugging these issues can be challenging. Now, let's discuss some key insights for interviews. A divide-and-conquer approach is often the most effective strategy for tree problems like this. By recursively computing the depth and identifying the smallest subtree containing all the deepest nodes, you can solve the problem efficiently. It's also important to focus on optimization during your explanation. Highlight to your interviewer how you minimize redundant computations by combining depth calculation and subtree identification into a single traversal, achieving an O(n) solution. Clear communication is another essential aspect. Make sure to explain your thought process thoroughly, particularly how you handle edge cases, and ensure the correctness of your solution. Starting with a brute force approach is fine, as long as you discuss how you plan to optimize it. Finally, since tree problems often involve recursion, you should be ready to explain how your recursive function works. This includes clearly defining your base cases, describing what each recursive call returns, and showing how you combine results from child nodes to build the final solution. For additional practice and understanding, there are several related problems you can explore. LeetCode 1123, lowest common ancestor of deepest leaves, is closely tied to this problem and involves finding the lowest common ancestor of the deepest nodes in a binary tree. Of course, revisiting LeetCode 865, smallest subtree with all the deepest nodes, is a great way to reinforce your understanding and explore alternative approaches to this exact problem. Another useful problem is LeetCode 236, lowest common ancestor of a binary tree, which focuses on finding the lowest common ancestor of two given nodes in a binary tree, a concept that has parallels to this challenge. Finally, LeetCode 543, diameter of binary tree, is another tree-related problem that involves calculating the longest path between two nodes in a tree. Each of these problems presents unique variations and techniques that can deepen your understanding of tree algorithms and recursion. Now let's consider alternative approaches and their trade-offs. One approach is the two-pass method. In the first pass, you compute the depth of all nodes, and in the second pass, you identify the smallest subtree containing all the deepest nodes. While this method is simpler to implement, it can have a time complexity of n squared, in the worst case due to redundant computations. A more efficient option is the single-pass recursive approach, which combines depth calculation and subtree identification in a single traversal. This approach has a time complexity of n and avoids redundant computations, but it requires careful management of recursion logic to ensure correctness. Lastly, there's the iterative approach. Using a level-order traversal or BFS, you can first identify the deepest nodes and then perform a reverse traversal to find the smallest subtree. While this method eliminates recursion limits, it can be more challenging to implement and debug, especially for complex tree structures. Each approach has its strengths and weaknesses, so choosing the right one depends on the problem constraints and your familiarity with these techniques. Thank you for joining me on this walkthrough of LeetCode problem number 865, smallest subtree with all the deepest nodes. We discussed the problem, analyzed the brute force approach, and reviewed its key concepts. Keep practicing these types of problems to strengthen your understanding of recursion and tree-based algorithms. Don't forget to like and subscribe for more tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!